Alright, welcome back to Quite Basic Math. Now we would resume the complex numbers, and we will be talking about the different forms in which your complex numbers could be written. Let's start with rectangular form. Now rectangular form is the one we are familiar with or are introduced to us, which is z equals to x plus iy. Right, so why is this actually referred to as rectangular? It is rectangular because this can be projected in your Cartesian plane this way. Don't forget your y-axis generically and your x-axis, right? And then if we project from the origin a complex number z, okay, please don't mind, it's not drawn to scale. So let's assume this is a parallel line to y-axis, so we can call this y and we can call this x, right? A portion of x. Then this line drawn here would be not just our z, the length would be the modulus, or what we call the magnitude of a complex number z. And the angle theta here, it represents the argument. So you'll see very shortly all of this notation. But the point is, okay, let's assume a right angle triangle drawn here. So if I complete this right angle triangle, if I complete this guy, look, you can see that it looks like a rectangle. It's not drawn to scale, so sorry about the lines not drawn to scale, but this is a rectangle. That's why it's called the rectangular form. Now let's answer all of this notation. Now modulus z, this bar with z, is called modulus or magnitude of z, of a complex number. And what actually it is the length of the actual complex number, okay, in the z domain, the complex domain. Okay, and you can evaluate it using Pythagoras theorem. Remember Pythagoras theorem? Recall Pythagoras theorem. Pythagoras theorem says that the square of Pythagoras rule, the square of the longest side, which is the hypotenuse, or the side that is opposite the right angle, 90 degrees, right, is equals to the sum of the square of the remaining sides. So it means that the modulus z squared is actually equals to x squared plus y squared. The square of this side and this side is equals to the square of this side, and this implies that modulus z is actually the square root of the real parts, don't forget, squared, plus the imaginary part squared. Okay, so that is the magnitude or the modulus of any complex number z that you are given to. Just take the square root of the sum of the square of the real and the imaginary part. Now that theta there, the theta you see there, is what we call the argument. Okay, the argument of z is the argument of a complex number. And the argument of a complex number is actually the angle between the complex number and the positive x-axis. Come again, it's the angle between the complex number and the positive x-axis. Alright, so that is your argument. You can write it, which is equals to the angle, okay, between the complex number z, angle between the complex number z and the positive x-axis. Okay. Now let me say this very quickly. There's something you need to understand, and that is the fact that sometimes when evaluating the argument of a complex number z, you might have a situation where you are working on the negative or the positive angle equivalence. What I'm saying is this. Now every angle can either be on the positive angle equivalent or the negative angle equivalent. Now this is what I'm saying. This is the 0 degrees mark, right? If I move this way, which you can call anti-clockwise, I have moved positively. If I move this way, starting from everywhere body starts from here, if I move this way, I have moved negatively. So every angle has its positive equivalent and its negative equivalent. Please take note of that. And to move from negative to positive, if you are on the positive side, you want to go to the negative side, you just subtract 362 pi. And if you're on the negative side, so you want to move to the positive side, you just add 360, which is 2 pi. Okay, Please take note of that. Now let's press further. So if I imagine I have a complex number z which is equals to x plus iy, assuming that this complex number z has the x to be positive and the y to be positive, that is if it is in the first quadrant, if it is here, imagine that the complex number is here, this place where I drew my line. Okay, now your complex number, the argument of that complex number, okay, at z will be equals to arctan y over x. Similarly, if x is also greater than 0 and y is less than 0, that is if it is in the fourth quadrant, if it is here, if you have a complex number to be here or here, they will have the same argument, arctan y over x, simply. But there is now an exception, or there are two exceptions. If your complex number z, x plus iy, is now in the second or third quadrant, if it's in the second quadrant, that is x less than 0, y greater than 0, this part here. That is, if you have a complex number that is here, it has a negative x and a positive y. Your arguments now will be equals to the arctan of y over x plus pi being 180 degrees. Okay, pi being 180 degrees, this is in radians. All right, and finally, if you have a complex number z that is equals to x plus iy, of course, where your x is less than 0 and your y is less than 0. So if you have a complex number z, say minus 2 minus I, a situation where both the real part and the imaginary part are negative. This is what I'm saying. If you have a complex number that is here, negative negative real, negative imaginary, in that case your argument of z, okay, will be equals to arctan y over x minus pi. Please take note of these expressions. They will help you to resolve the argument of any complex number very easily. Now let's look at some special cases. Just put them down. We'll make use of them when we start solving questions. Now, what if I have a complex number z that actually does not have a real part, that just has imaginary parts? Is 0 plus or minus iy. Now, if you have a complex number like this, a complex number, let's say iy, or a complex number minus iy with no real parts, the argument of such complex numbers, right, will just simply be plus or minus pi over 2, that is plus or minus 90 degrees. Okay, this is in radian measurement of angle, and this is measurement in degree. So pi over 2 plus or minus pi over 2 plus or minus 90 degrees represents the argument of any complex number at all that does not have a real part, but it has imaginary part. So if it is positive imaginary, what I mean is, if you have z equals to I, z equals to 20i, 40i, 100i, you have pi over 2. And if it's a situation where it is a negative imaginary part, you have negative pi over 2, irrespective of how large or how small the imaginary part is. If it is 1000i, the point is, so long it doesn't have a real part but has an imaginary part that is positive, the argument will be pi over 2. And if it is negative, minus pi over 2. This is the first special case. Now in the second special case, if you have a complex number z, now you might want to argue that, how is this a complex number? This is a real number. You begin to understand that that complex numbers is actually the big umbrella, and real number is actually a subset of complex number. Now the reason why it is so is because, don't forget that we said every complex number z has a real part and an imaginary part. So actually a complex number is a superset of real numbers. So now if I have a complex number, yes, permit me to say complex number that does not have an imaginary part, funny as it sounds, but let's assume you have something like this. Let's say a complex number that is basically real. So you have x, plus or minus 0i. This is what I mean. So you have a complex number with no imaginary part, but just just this, say z equals to x or z equals to minus x. So if it is positive or negative, okay, just like we did for this case here. Now if it is positive, all right, if it's a case where it is positive, that is for this one, your argument is gonna be you can use that to use 360 degrees, if I'm not wrong, 360 degrees or 2 pi, okay. And if it is negative, it will be 180 degrees or pi. All right, so any one of these would always be the arguments depending on what you are dealing with. Okay, now I think enough of that. Let's quickly, now I know you might have been thirsty for questions, that when do I get to answer questions, solve examples. What I'm trying to do is that I want to teach all that there is for you to know, and then we'll start solving questions. But if you are so thirsty to solve questions, well, let's quickly see one then, to at least calm your nerves about the questions that you have or you'd like to see. And look at this question. They said z equals to, let's look at an example. Z is given to us to be equals to 1 over 1 minus root I, and then we have to evaluate the modulus. We have to evaluate the modulus and the principal argument, of these complex numbers. Okay, now the first thing you want to do is rationalize this. You know, this is a complex number that you have a form of division. So if you rationalize this guy, you'd have times 1 plus root I over 1 plus root I. This will be equals to 1 plus root I over 1. Don't forget what I said. When you expand this, just be this squared and this minus root I all squared. Okay, this will be 1 plus root I over 1 minus I. Okay, and your z now be equals to 1 plus root I over 1 minus I. Now from what you have here, okay, to find the argument of this, to find the modulus first, the modulus of this, you can use the rule of modulus. Okay, that takes us to, okay, something I have not discussed though. Note that if you have the modulus of two complex numbers like this, all right, it's the same thing as the modulus of all of them together. This. So take note of this rule. If you apply that rule here, the modulus of z, which is equal to the modulus of 1 plus root I over the modulus of 1 minus I, this will be equal to the modulus of 1 plus root I over the modulus of 1 minus I. Right. Okay, well, there's a principle that I would need to actually explain to be able to solve a question like this. All right, so let me put a pause to this example and move on. Let me put a pause to the example and move on, because if I begin to draw some inferences from here, you might get confused. Okay, and I've not discussed it already, those inferences. All right, so let's move on. Now, another thing you need to understand is the concept I said I was going to talk about, this property. Now, if you have a complex number z multiplied by its conjugate, don't forget what we said about complex number z, x plus iy. So if I multiply x plus iy by its conjugate, you will see something here, something very interesting. Now, don't forget this will give us x squared plus y squared. Now, don't forget that we have seen this guy before. This guy is actually the modulus of the complex number squared. So which implies that if I actually multiply a complex number z by its conjugate, I will get the modulus of that conjugate of that complex number squared. So this is an important rule that you make use of when evaluating or simplifying some complex number algebra. Okay, please take note of it, because it will save you someday. That there would come a day that it might save you a lot of problems. Let's proceed. Let's look at other forms you can present a complex number. Now there's something called Euler form, or some other people call it exponential form. There are complex numbers that can also be presented in Euler form or exponential form. And how do we do that? Now, if you have a complex number z, don't forget we said is equals to x plus iy. You can also write it in Euler form. How? This way, modulus of z e I theta. We already know what modulus of z is. I know what theta is, the argument. Or some people write it as r e I theta. R means where r is simply the modulus of z. Okay, so this is your Euler form. Every complex number z can be written in this form likewise. Also, we have something called polar form. Polar form though can be in various forms. You can have a polar form this way, r theta form, something like this. Could have your polar form this way, r comma theta, like this. Could have your polar form this way, what we call polar trig, r into cos theta plus I sin theta. Do not forget what r is. R is the modulus of z. Okay, so your polar form could come in all these forms. You already know what r is. R is modulus of z. Theta is the argument of z. Okay, theta is argument of z. So any complex number can be expressed in all of this form. Once you can know the argument of a complex number and its magnitude, then you can present it in any form as you deem fit, as you need to. Okay, as the case may be. And let's proceed. Let's talk about higher powers. Let's look at some higher powers. So what do I mean by higher powers? Now if I have I raised power 1, I raised power 1 is I, right? What if I have I raised power 2? I raised power 2, we said I squared is minus 1. What if I have I raised power 3? I raised power 3 is I squared from the law of indices times I. And I squared is minus 1. So I'm multiplying it by I, which is just minus I. What if I have I raised power 4? I raised power 4 is I squared times I squared, okay? I raised power 4 is I squared times I squared. And I squared is minus 1 times minus 1, which is 1. Then what if I have I raised power 5? I raised power 5 is I raised power 3 times I raised power 2. I raised power 3, we did it here, is minus I. And I squared is minus 1. So that means that I raised power 5 is simply I. Now you will realize something. Let me continue. Okay. What if I have I raised power 6? I raised power 6 is simply I raised power 3 times I raised power 3, or I raised power 4 times I. However way, I raised power 3 is minus I raised power 3 is minus I. So this will give us I squared, which is minus 1. Now I raised to power 7. I raised to power 7 is I raised to power